Hello. Hey, periodicity part two. If you haven't watched part one, watch part one first. Main focus of this is going to be electron affinity. But let's look at something, just to review some things about atomic size and things like that. Okay, so let's look at oxide versus fluoride. Which one's smaller? Which one's smaller? All right, so tell you what, why don't you pause that video and just think about it. Look at your periodic table, think about it, see what you can do. All right, did you get it? Well, let's figure it out. So, we know oxygen has 8 protons, fluorine 9, oxide has 10 electrons, so it's 1s2, 2s2, 2p6. Hey, isoelectronic 2, neon, yeah. Hey, fluoride, let's see. Plus 1, 10 electrons. Hey, same number of electrons, okay? So what's going to be the difference here? I think you guys got it. It's number of protons, right? Oxide has 8 protons, and fluoride has 9 protons. So we have 2 electrons here in the first energy level, 8 electrons here, okay? Then, so the 9 protons, that nuclear charge is greater. It's gonna pull electrons in a little bit closer. I don't like my drawing, but fluoride will definitely be smaller because the nuclear charge is greater. Another thing you can do is look at the effective nuclear charge. The effective nuclear charge, 8 minus 2, number of protons minus the core electrons, so that's 8 minus 2, so it's plus 6. Fluoride will be 9 minus 2, so it's plus 7. That effective nuclear charge is greater. Kind of tells you that that's going to be smaller, okay? All right, thought I'd start with that. Let's look at electron affinity. Electron affinity. Let me erase this. Look at that word affinity, liking for, right? What atoms like electrons? What atoms like electrons? Yeah, non-metals, right? So let's look at definition first. So it's basically, if we have an element and we push an electron into it, we'll get an anion, and some energy will be released. So the more energy, the more attraction the atom has for the electron. Okay, let's think about that. The more energy released, the more attraction the atom has for the electron. So let's look at the halogens. I think we should look at the halogens first. So let's look at fluorine, chlorine, bromine, okay? If we're thinking about bromine, of course, it's argon, what is this? 4s2, 3d10, 4p5. So it'll definitely receive that. Bromine will be attracted to an electron to become -1, and of course it'll release some energy. Okay. Now let's compare that energy with the energy associated with chlorine receiving an electron. Well, chlorine's smaller, right? Chlorine's smaller. So when this electron is being added to that p orbital, of course we know there's a nuclear charge there. Think about which one of these electrons is going to be more attracted to the atom. Well, it's going to be chlorine. Since the atom's smaller, that electron's going to be close to the nuclear charge. Remember that Coulomb's law, force of attraction's directly proportional to the charge of the electron times the charge of the nucleus divided by the distance. So if we decrease the distance, if this gets smaller, right, denominator gets smaller, the fraction gets larger, force is greater. So chlorines, so the general trend is when you go down a group, the electron affinity goes down because the atom is getting larger. There's less attraction that electron has for that atom, all right, or the less attraction the atom has for the electron. Fluorine's a little different. It turns out this chlorine has the highest electron affinity on the periodic table. The reason fluorine does not, okay, fluorine is especially tiny. So if you think about adding an electron there, sure, that atom's gonna attract that electron, but this electron is coming into an area that's pretty rich with electrons. And what do these electrons do? This electron repel. And that's why fluorine's electron affinity is a little less than chlorine's. Chlorine's is the highest. It's because that atom is especially small, and that electron's getting repelled by these electrons. Sure, it's getting attracted to the nucleus. Sure, it is. It's going to release that, right? But that's an exception, okay? One more thing we should look at is nitrogen. Let's look at that over here, nitrogen. So we have 2p, so we have this. So what do you think? You know, if we throw an electron in here, there's an electron already in this orbital that's going to be repelling that. And what do we say about half-filled orbitals? Atoms like half-filled orbitals, right? And filled orbitals. So nitrogen virtually has a zero electron affinity. It doesn't have an attraction for an electron. It's true for the noble gases as well. Noble gases, their outer energy levels are filled, and there won't be an attraction. All right, I think that's all I want to talk to you about in terms of electron affinity. I hope you understand that the more an atom has for the greater the attraction an atom has for an electron, the more energy is going to be released. Okay, the greater electron affinity. Electron affinity is associated with the energy released when an atom gains an electron. All right, thanks.